Hi. So, hello and welcome everybody to this edition of Akhan Data Science Meetup. Today's theme is about data integration and pipelines, as you can see on the screen. The motivation behind this theme was really the challenges that we have when we handle data, especially in life science and biotech industries. Even now, the Excel and the text files, the flat files, rule this world of research. And it's a real challenge to integrate this data from different sources, given the complexity and variety of data that gets generated nowadays. And the real value of data will be realized only when we look at the complete cycle or the life cycle of the data as such. And this is where these steps of data integration and data pipelines comes into picture. So that was really why we decided to have the meetup on these themes today. Before we jump on to our introduction of distinguished speakers, I would like to introduce a bit about myself. So, yeah, I am Nikhil Damle. I am a senior consultant working in the area of bioinformatics and life science at OSTRUS. I have joined OSTRUS since 2019, and before that, I had an academic life. I did my PhD in bioinformatics from India, and then I did two independent postdoctoral research stints, one in Stanford University in the USA, and then in Freiburg University in Germany. And at OSTOS, I am involved in various projects related to data integration, data visualization, modeling, and of course, bioinformatics. And I love programming and developing in Python, Perl as well. Now, to say something about our company, who are we and why do we host these meetup events? We are trusted partners and service providers to our customers and clients in the pharma and biotech industries, and we are active in the area around data when it comes to data management, when it comes to data insights through, for example, analytics, or when it comes to data strategies, how to organize your data, how to data architectures, all those things. And of course, recently, data governance. When it comes to these data related aspects or challenges, our clients, some of which are listed on the slide, they really turn to us for these things. With more than 2 decades of experience in this field, and our experts are involved in different projects, and we help our clients and customers to really build long lasting solutions centered around data. We mainly provide consulting and solutions around data with these expertise as I have listed. Now, uh, yeah. So now we come to today's theme of the topic, or the today's theme of the meetup, which is data integration and pipelines. And as I said, we have two distinguished speakers with very exciting talks. Our first speaker today is Yifang Chao. He is a software developer at Ostrus since 2019, and he is an expert in the field of DevOps or when it comes to cloud, etc. Apart from that, as an interesting fun fact, he is really interested in martial arts, and that's what he's going to talk about today, isn't it, Yifang? No, I'm kidding. He is going to talk about how do we as Ostrus, or how does he build data pipelines from scratch and in cloud. So handing over to you, Yifang, I will make you presenter.
Yeah, thanks, Nico.
Yeah.
Thanks for the introduction. Yeah, you have to make me
And
the
you
present.
are the presenter now, so you should be able to present your screen.
Okay, thanks.
By the way, if you guys have any questions, you can also put them in chat and we can take them after each talk. And as I said, at the end also, there will be opportunity to ask questions. So over to you, Yifang.
Okay. So hi everyone. Thank you so much for joining today. So I'm here to talk about one of the most fundamental components of data-driven business and data analytics, which is data integration, as Nico mentioned. So a lot of companies or organizations nowadays are kind of struggling to manage their data and make sense of their information. So because their data are typically disparate and scattered all over the place, this is where the data integration comes in. So data integration is a process of combining data from multiple sources, typed into one unified and consistent model or view. Um, this typically involves extracting data from various sources, transforming it to uh, a unified data types or some data models, and also loading it into a target system, usually a warehouse, data warehouse, a data lake. And data pipeline is actually a way to achieve data integration. That's the main focus of today's talk. And so data pipeline is typically a series of automated steps. I know Nikhil mentioned we're gonna build the pipeline from scratch, but that's actually not quite true. I have pre-made a couple things, but we're gonna dive into the actual the tools we are using. Um, so let's get to the contents here. So in this talk, I'm gonna present an example of the data integration and data pipeline, which was taken from a real project our company is currently working on. So this project, this example you're gonna see has been simplified. I hope it is very easy to follow for even for those of you who have little or no background knowledge about data integration or cloud technology. So I'm gonna start with a brief overview about the project, and then I'm gonna talk about the goals that our customers are trying to achieve. So our customers have a lot of questions on their data, and they want to get answers from that data, but that's quite difficult for them to kind of get the answers they want without data integrated. Um, and lastly, I'm gonna present the solutions currently we're working on with the customer, and also the services um, on the cloud, and also I'm gonna present the kind of a simple architecture for the solution. Okay, let's get to that. So the project is mainly about helping some scientists to analyze the study results about nuclear radiation on humans. So basically, they want to know, let's say a nuclear bomb goes off and some people are exposed to that, but they don't really have like symptoms, like obvious symptoms in some time, and they want to kind of know without the symptoms how quickly they can.
So thinking about what is the range that the rates that I would.
Yep. Sorry, please mute yourself if you have not. We have a question session, I think, at the end of my talk, and also at the very end of all the speakers. Okay, let's continue. So basically, they want to know if some people are exposed seriously for a nuclear exposure without any symptoms. So they have conducted a study on the human exposure on that nuclear radiation. And so in this simplified presentation, I'm gonna just present. Let's assume they have only gathered like two types of data. So they actually have quite a few different types of data um, in reality, but for simplicity reason, let's just assume they only have two types of data in this presentation. One is the animal demographics, so basically the animal they used in the study, and also the blood sample data, which is the blood sample taken after a radiation test. They are both data. So both data types are both data files are linked, and I will say why that's causing some problem in this case. Just a side note, all the data I'm gonna present in here is not real data, just for confidentiality reason. Okay, let's go to the next one. So as mentioned, they have um, animal data, which is a representation or a table. Actually, they are tables. On the left, the animal table. They are the animal used in the study. We have study ID and animal ID. That's the unique identifier for an animal, and the group, and the start date, study end date, the sex of the animal, and then here's a link to a blood sample ID. That's uh, actually this column actually links to the other data file, which is the blood sample data here. The very first column is the ID for that blood sample, and then we have a bunch more columns. And in here, the only thing we care about in this example, in this talk, is actually the white blood cell count, or WBC count. Um, yeah, just two simple files, but um, the scientists, let's say, they have a question, very simple question. They want to know which animals, let's say, which animals have this white blood cell count over 5,000 in February 2023. Um, yeah, if we just look at the table here, it's actually quite easy to find out if we just compare them side by side, right? We have this column here, and we know starting from here, 5,100, those are the ones over 5,000. And we have the date column here, right? Probably the bottom three are the ones we are looking for, right? So that's actually a question that can be answered easily, but don't think about this simplified situation, but just think about the real world. You won't necessarily always have somebody just opening two files on their computer and just compare them like manually, right? And there could be thousands of data files in there, and each file can have like thousands of rows. So there's no way you can do this manually just by looking at the data and just do that. And although it's not very easy to kind of query on this, like automatically or programmatically, because those two files are obviously not in the same format. And if I just open that, let's say blood sample data, I have a real data here. You can see that's just a text file. There's no way you can query on this. You have a lot of distraction here. You can see the dashes, probably something you don't need, some footnote. Um, so overall, that's not structured data. So we cannot just answer what is the over 5,000. There's no way we can do that. And what's the solution for that? So actually what this guy is, is really trying to do is he's hoping um, he's got like two tables, not really two raw data, right? If somehow on the left, that table is a table in a database, and also same for the right, the file on the right. Um, so this guy can really do a query, right? Uh, Basically, just select the animal ID from the two tables. Just do a simple join, or the where condition here. Just join by the sample ID. And okay, that's actually a typo here. That should be greater than 5,000. So blood, the white blood cell should be greater than 5,000, and then you can do a filter on the date after February 2023, right? So that's actually the goal they want to achieve, but without tables in the database, they cannot do this, right? So what's the solution for that? if we get to the solution, we have to split uh, the question into like different aspects. First of all, we have the data files, and we have to think about where we're going to host the data. Um, so the data can be generated by different facilities. They're not necessarily on the same computer. Then that's actually one difficulty. How to bring data together first, right? Before we even do any kind of transformation or uh, integration. And the solution for that, so for that can be, as I mentioned, our solution is on um, AWS. So solution for that will be Amazon S3, which is a storage service, and it has a bunch of advantages such as scalability and availability. Basically, that's a uh, publicly available service. You can access it anywhere from the world, and basically those scientists, even they are located in different facilities, they can always log into this service and can drop their data to this online cloud storage. And another advantage is that it has permission control. So each user will be granted with some permissions, so they cannot delay somebody else's work, and they can only focus on the part um, they are uh, they are granted the permissions with. And the next question, next difficulty is that as we have already seen that the data format is needed. Typically we transfer transfer to JSON, and
Yifang, we don't really. Ah, okay.
can you hear me now?
Yes, we hear you now, and we also see your
Okay.
screen. Go on.
Yeah, sorry about the disconnection. So basically the second point is we have different formats. We have the Excel format, text format, and we want to kind of transform into a unified format so we can use them really in the end. And the solution for that will be, if you know Python or any programming language, you can just write a program, kind of parse the raw file I just presented before right here. Just get rid of the like vice spaces, get rid of all the dashes, footnote, and everything. Just make it a CSV file. Let's say CSV file. That's the target file, right? Um, the question is how and where you're gonna run this Python script. You can run this on your local computer, but since the data is not in your computer as a programmer or developer, um, they are in the different facilities. So the solution for that is AWS Lambda. That's a serverless compute service. What that means is that you can upload your program just as is without managing the underlying infrastructure. Like so you don't have to deal with the server configuration, things like that. And it has a great integration with S3. I'm going to show you in a moment in the end and how you can achieve kind of real data, almost real data integration with Lambda and S3. And lastly, even we have the CSV files, they are still not queryable. They're unified, but um, they're still like text file. So some services we can use on AWS are the AWS Glue and AWS Athena. It will, so basically AWS Glue, that's a service with that you can apply the schema on the CSV files. So that will make your text files, text files into a like database-like environment or something queryable, right? And then Athena is actually the query engine for that. So that's actually a kind of architecture for this setup. Um, so you have like two types of data, and you can set up S3 for each type of data. Each S3 can have different permissions. For animal, maybe they belong to the animal facility. For the block sample, they are maybe part of the hematology facility. So each facility can have its own bucket and has its own permission and upload their files to different buckets there. That's on the left. That's the storage layer. And for each bucket, we can set up a trigger to trigger the lambda function, basically the Python script you have for transforming the data into um, the targeted format, which is CSV in our case. And both lambda functions can dump the data to a process bucket that's a separate bucket will be only used for query purpose. And then you apply glue data catalog, which I mentioned, that's a schema service. You can apply schema on CSV files. And once you apply the schema, and the data in the bucket um, become queryable, and then you can make the query after data. Let me really quickly show you everything I have on this page. So I'm gonna just open the console. Just let's look at the storage layer first, right? Um, so basically this, so that's if you have never seen this console before, that's the S3 page console for the S3 storage service. In here, you can create different bucket. Each bucket is a isolated kind of space for a bunch of files, objects. And I have set up one for animal, which is this one here. And it contains the raw data for animal. And I have another one for blood sample. This one contains the raw data for blood sample. And the last phase, so that's the second phase for this pipeline, which is Lambda function. So Lambda function is in another page here. So each function here means a application. That's literally a Python script you can put in here. So for a typical data integration Python program, you will have like get the data phase, get the file action, transform the data. You can do like save the file to the processed bucket, and that's where you can just write Python code in here and run it on the cloud without any like server management hassle. As I mentioned, you can set up a trigger really easily just by clicking that, set up a trigger. For the source, it will be S3. And you can listen to a bunch of different actions. So maybe in this case, you are interested in file uploading or basically file creation. Whenever somebody uploads a file, you want to trigger your transformation Python script. That's the way you do that. Let's just do that. You can pick the source, right? You can maybe this is for the animal transformation. You can pick that, and you can just add it. Very easy. That achieve this thing here, trigger from the bucket to the Lambda function with your transformation script. And in the program, you can write the transformed file into the process bucket right here. And process bucket, let's look at that. So I have one for the transformed animal, one for blood samples. They are in CSV format, so they are ready to be used by ADSM Glue. And if I go to glue, I'll show you what that means by applying schema. So it's like a database here. That's one way to use that. There are many ways to use AWS Glue. So in this case, I'm just gonna present this way, with applying a schema to a CSV and then make it queryable. Just like normal databases, you can create a database. In this case, I have already created that. For tables, each file can be a table. And the good thing about that, it has also S3 integration. So you can just specify the location for the bucket. And you can see, I mean, just expand that. So the location for the animal will be the animal bucket. Actually, not the bucket, actually the processed CSV files in the process bucket. And blood sample will be pointing to the blood sample location. And if I kind of open that in
E-
here, you can
Yifang,
configure. Yep.
Yifang, I would just like to
Yes.
remind you that you have 5 more minutes.
Yeah, sure. We'll be finishing that. So that's a quick page on here. You have the schema. Let me just quickly open that, the processed, or maybe I can go back to the slide here. Oh, sorry. Okay, give me one moment. Can you still see my screen?
No.
No? Okay, let me reshare. Okay.
Now, yes, we do see
Okay.
my screen.
So let's open that. So that's the processed CSV here. We kind of shrink the data down to just 3 columns. We're only interested in date, the count, the blood IDs, and we apply the schema in here. Okay, we have 3 rows in here. First one that can be you can apply just indicate the name for the column, the data type, and here we go. That's it. That's all we have to do to kind of apply the schema. And once we have the schema ready, if you go to the Athena page, which is the query engine here, you will see the tables showing up in here. Right? They are just like regular relational table here. And you can just query that. Let's just review the table, except for blood samples. Right? You can see the content for that CSV in here. And if I go back to slides, just remember this guy has this question here. He needs to run this query on the target table, right? Let's just do that. And that's a SQL query. Just run that. And then what you get the intended answer, right? That's the original one we are seeing here. Those 3, animal 10, 11, 12, right? Just by running the query against the database. Yeah, you get the answer here. So this way, that's a scalable way to that, and you can apply this pipeline to a huge amount of different sources, just add more like structures, and you can make this even more complex. Just feeding the process data as the source. As for another pipeline, that's something you can also do. You can also maybe the output for the Athena query, you can also feed that into a different pipeline, and just do something crazy. Okay, I think we are running out of time. I think that should wrap up my presentation here.
Yes, indeed.
Yep.
Okay. Thank you, Yifang. I was really impressed to see the ease with which you were handling different services and querying in AWS. This is good to see the way the pipeline has been established in cloud. In the interest of time, I propose that we move ahead to our second speaker because there has been a last minute change. Our previous speaker, Dr. Mark de Graaf, for various reasons could not be here today and could not present. But graciously, Dr. Matthias Nolte accepted our invitation to present what he is working on chemical structure data because and how he is integrating chemical structure data using Chemantics. He is the CEO of Chemantics, which was recently founded in 2022, and he is an expert chemoinformatician with more than 2 decades of industry experience. And he also plays trombone, a musical instrument. And today he is going to talk about how he is addressing some of the major challenges in handling chemical structures and his solution using Chemantics. So over to you, Dr. Nota. I will make you presenter.
Thank you, Nikki. Let me share my screen.
Yeah, you are the presenter. And we see your screen.
Wonderful. This one, right? Yeah. Yeah, when you mention I have 20 years experience in cheminformatics, all that really means is that I'm really, really old. So I apologize for that. Anyway, yeah, I'm Matthias Nolte. I also am a consultant with Ostus, so that's where the relationship is then also to this meeting. But here I'm going to speak today on behalf of Chemantics, which is a company I co-founded last year. So we talk about semantically enabled chemistry here in this context, and chemistry is interesting in itself as a informatics area. There's a discipline, cheminformatics actually, which you can study. So it has very specific needs from the chemistry perspective and the IT perspective as well. And I'm not going to talk about many of those things though, and I assume that most of you don't really have a chemistry background, so I'll try to keep it a little simple. But I want to get the process across and the principles. In order to do this, I put on a typical use case which I've seen in my career over and over again, and it's really around the fact that a scientist nowadays, and 20 years ago as well, asked, how do I identify all the chemical structures which are relevant to my current chemical structure of interest? And I want to do this because I need to enhance my knowledge about this compound one way or another, right? And that manifests itself typically in other questions like these here. For example, does my chemical structure already exist in our corporate database? Has it been registered in our registration system, for example? That will be a question which is embedded in the upper question there as well. Does my current research overlap with public data? A big issue in the industry is that there's a lot of data out in the public domain around chemistry. But if you work in an organization like Pfizer or BMS, it's actually frowned upon, if not forbidden, to actually use your chemistry expertise and search, do Google search or search in other databases with that chemistry, because that chemistry is highly protected for intellectual property. And that really makes it difficult to find the relevant public data because you don't want to disclose in the queries what you're working on. A huge problem. That's why a lot of the data in the pharma industry actually gets ingested into the organization as well, as opposed to being used outside. Also, when you look at mergers and acquisitions, when I work at Pfizer, Pfizer has a huge history, a long history of acquiring other companies. There was a big merger just about every 2 or 3 years when I was there. And one of the big assets they want to get to is not the people. It's the IP, which is hidden in the chemistry. At that time, they were all chemistry companies. The question is, if I buy an asset from a company, whether it's a data catalog or a company at large, how much is the overlap to the data which I already have? And is it actually worth acquiring this company if there's only, let's say, 10% of extra new data which I'm getting? And I'm only talking about chemical structures here, right? That's a huge problem, and I've had to answer this question many, many times with a whole team of people, and it's always been very difficult and time-consuming to do because these companies, they don't want to share their knowledge, for example, prior to a merger. They want to keep as much to themselves, and if the merger doesn't go through, then they've shared all the knowledge, and the IP is not protected anymore, potentially. So a very difficult situation there for both parties. And then as of recent, as I'm working with the Pistoia Alliance, which is an alliance which is very much emerging in the scientific community and the pharmaceutical community, questions around which substances are used as an active ingredient in a product, in a medicinal product, and what is the parent compound this substance belongs to. So there's some terms which I'm using here, parent and compound, active ingredient. These are all relating to individual compounds or a mixture of compounds which represent the pharmaceutical compound you take as a medication. There's a global substance registration system which the FDA has put together a few years back. They maintain that data, has about 100,000 structures in it. It's not a large database, but it very much captures the chemistry which enters our body through medications typically. And the EMA, the European Medical Agency, is very much involved there as well, and the World Health Organization too. So in this project, we're actually trying to find out what is actually a unique chemical substance, because the question of uniqueness is still a decent problem in the chemistry space. And the problem lies in that chemistry is actually chemistry, right? Chemistry is not trivial. We're dealing with three-dimensional objects. In the database system, they're typically reduced to two-dimensional representations as a standard. For most people, there's still three-dimensional aspects of chemistry. For example, if you look at crystallography studies or molecular modeling studies, which are all in 3 dimensions, but the chemist in its day-to-day work, he doesn't think in 3D. He thinks in 2D because it's practical for one, and it describes exactly how the chemist thinks. So this is a representation which works with the chemist's mind very well. I just don't know whether it's because we are used to 2D representations and that makes us tick, or it's the other way around. I'm not quite clear on that yet, but it doesn't matter. And but we also use then the 2D representation to communicate chemistry and chemistry knowledge as well. Now that could look like this, for example. These are all representations of the same molecule. On the far right, I'm going to start on the right-hand side. That's a molecule which I took up from my notes today. Actually, I draw this out, and I know exactly what that means. It's orthoxylene, and that is a very dirty drawing. It's a scribbled note, which of course doesn't mean much to a lot of people. But if you are a chemist, you can actually figure out what that actually is supposed to mean. It actually means this. That's a standard drawing of the same molecule, right? We can fill it out a little bit, where we only have the carbon dots here at the end. We have hydrogens now here for the terminal groups, where they're called. And then we can also go to a 3D representation of the same molecule. And these have different levels of accuracy, of course, right? And whenever we go from right to left, we lose accuracy, and then also we lose information with the accuracy, of course. But it's an abstraction process which is really needed because it's pragmatic and we use it all the time. And nobody's telling us that this is actually the exact representation of a molecule as well, right? So the metal group's actually rotating like crazy around this bond here, and there's no way in pinpointing them down, at least not in liquids or in gases. What's the right representation of a chemical? It's not easy. But what we're dealing with, 98% of all the chemistry data is actually done at this representation here at this level. So when we look at notations, how do we get these into the data systems? And I apologize to all of you who know this very well already. There are 2 formats which really have stood out in the past. One is the SMILES notation. It's really called SMILES. It's the Simplified Molecular Input Line Entry System from a company called Daylight. They came up with this, and that is a line representation of this benzene molecule over here, and that describes exactly in this line of notation what this looks like. So chemists who use this a lot, they can draw this by hand, or they can look at the structure and see where abbreviations are and what this looks like. Another common version is the mol file, the molecule file. Looks like this, has 3D coordinates. In most cases, the Z coordinate here. In this case, this column is 0, so it's actually a flat representation. So we have atoms here, they are carbon atoms, CC, CCC, and then we have bonds between these. So between atom 1 and atom 2, we have a single bond. Between atom 2 and 3, we have a double bond. So all fine and well. The question is, how do you know that these 2 representations are actually identical? Fortunately, there are conversion programs which can deal with these issues, and they do this actually quite frequently and quite well, but not always. The issue becomes more complex when you draw benzene like this with a big circle in the center, which depicts the aromaticity of the molecule, which is a very specific chemical concept. And there you have this notation here for the smiles, and then this notation for the mol file, where everything is identical in the mol file except for the bond. It's a 4, which indicates an aromatic bond, and the coordinates are all the same. Actually, these molecules are exactly the same, right? They are not only shown differently, the representation is differently, but they are in fact the same. So one of the challenges is to make sure that these molecules we look at, or the data we look at, is actually identical if we want to link data together based on chemical structures. So I'm using this with a very simple example, of course, and there are many, many more difficult ones. And for example, in order to then make sure that the data actually becomes independent of these representations, the IUPAC has been sponsoring an initiative called INCHI, which is International Chemical Identifier, which is calculated from the structure. And as you can see from these two depictions, the identifiers, the INCHI string and the INCHI key, as they're called, they're actually identical here. So this notation now is used to link chemistry data together on the web a lot of times. Wiki uses it for some things, Google uses it well, but it's still not perfect. And the question really is this a sufficient tool to make good data analytics and prepare data for good data analytics? For example, what do we do with tautomers? Tautomers are molecules which look like these. So these are 4 tautomers. And if you look at them carefully, so you see here you have a double bond to the oxygen here. Here you have a single bond to the oxygen, but here you have 3 double bonds in the ring. Here only you have 2. Here only you have 1. And if you look at the INCHI codes here, they are all different, right? So in the second part, we have WQ, PTA, SX, and FLQ. So the INCHI key will actually tell you that these structures are different structures. But in reality, tautomers are actually fluctuating from one representation to the other. So there's actually an equilibrium, possibly between all 4 of these. None of these is wrong. They're all correct, but the question is which one is the most dominant one, right? And most of the times we don't know this until we do very accurate measurements. But the point is, if we look at different data and different databases, nobody prohibits you. Nobody would look at you in a weird way and say, "This, you do it this way? Are you crazy? It needs to be this way." They're identical for all intents and purposes, right? But it makes the linking of compounds very difficult. So what we're trying to do is remove all these obstacles so we can have a true identifier which helps us link the chemistry data together. Another class of molecules which is very interesting and very complex and important are isomers. Specifically down here, enantiomers, these are molecules which behave like a left hand and a right hand. They don't overlap, they're mirror images of each other. And for some of you who are old enough, you might know the example of thalidomide, which is a product from Grüntal, which caused birth defects, because the drug which was out in the market was a mixture of the 2 mirror images. Even nowadays, if you look in the literature, the data for thalidomide still does not distinguish between the plus and the minus, or the left and right hand of this molecule. So we need to be very careful when we aggregate data, because you don't want to create data sets and aggregate them where you have molecules which really don't belong together. It could cause real problems, specifically the medicinal work. So what we do to avoid this is we carefully identify these and generate the identifiers, and then we create relationships where we say this molecule is an enantiomer of another one. In this case, it would be between the 2 instances of thalidomide, for example. So there are a whole bunch of these. And this is just one chemical class which we're representing here, which makes the chemistry space actually fairly complex and definitely not boring from an IT point of view. So from a system point of view, what we do is we have developed a classification annotation server, we call it. It's an engine which basically ingests data from different data sources. So GSRS, as I mentioned before, from the FDA. It could be a local data set. These here, the examples are all pharmaceutically related, but it could be any data set which is related to chemical structure. And we load these in, and we analyze these data. We normalize them, make sure that we compare apples with apples and oranges with oranges, as we say in America, and annotate these then according to what the findings are on these molecules and what their chemical classes are. Then we organize the data and have APIs then which allow access to the data in the cloud to get access to what you need. You can integrate the data then and organize in different ways. I'm not going to go into details here. It's very flexible from that point of view. And we do all of this by using a fair data infrastructure in the backend. So we're FAIR compliant, we think, for the most part. And we do this by using persistent identifiers for each entity in the system, by using standard communication protocols, have vocabularies and ontologies which can be shared with other parts of the organization as well, which use our data. And then we have a very strong emphasis on data provenance as well. So for every data point which you look at in the system, we know exactly where it comes from and how it relates to other things. So we really talk about a semantic chemistry integration engine from that point of view. And as I mentioned before, it not only looks at a data set within your organization, but it can look at data which and link data together based on any data set which you think is interesting to your organization. So what we do is we have different modules to accomplish all of this. There's the registration module. Here we normalize the structure. We generate a PID, which is a persistent identifier, which is linked to the structure and actually calculate from the structure, which is really important. If we just give an identifier 1, 2, 3, and we do this at another company or another data set, we wouldn't know what this 1, 2, 3 actually means. But we can calculate the data at Pfizer or at BMS or locally on my machine. And for this molecule, I always get the same PID. That then lets the data systems be created independent of each other. And then when you need to compare data sets, you can just share the PIDs and see what the PID overlap is. So you don't share any information actually. So where you have overlap, you share information with the compounds the customer or the other partner already knows of because the PID matches. If it doesn't match, you have a PID and you don't know what to do with it if you don't have the data. So that helps with the mergers and acquisitions aspect, just this piece alone. This is a little bit on the organization of the data. We can create virtual data collections, which then can be searched and brought to the user in a more user-friendly way through virtual aggregation. It's all done through our semantics, where we say a data set is part of another data set. Then where it becomes really interesting is in the annotation module, which we have. We have about 17 annotation types which we calculate. Some of them are very much standard. So which rings systems does this molecule have? But also we look at scaffolds, which are very important tool for analysis of chemical data and those kind of things. Some of these are very well known and others are proprietary to what we are doing. The classification engine then goes a step further and looks at the molecule in great detail and classifies it based on the chemistry it actually depicts. So here we identify functional groups, alcohol groups, whether it's a hydrocarbon, whether it has amino acids, for example. Those are identified, and those are then all searchable in the context of a chemical structure. So when you do a chemical structure search for benzene here, and you do a substructure search, as it's called, that is the equivalent of searching for the letter E in a 5 million document database. So you get every document back, basically, right? Benzene is de facto part in 90% of all the chemical structures which are of pharmaceutical relevance. It's just there. So you don't really want to make a query like that by itself, and you don't find anything meaningful because there's just too much data coming back. But you can combine these with our classifications, and then you can say, show me all the molecules which have a benzene, but it also should contain 3 amino acids in a row, and one of them needs to be a tyrosine, the other one needs to be a lysine. I don't care if it's the first one or the second one, which is the lysine, but they need to be in a row, for example. And those are queries which you can express in a chemical structure drawing tool for a search engine, but they're very difficult to write, they're very time-consuming to write. And by our classification engine, this data is just on your fingertips. By creating the query, basically, you browse through a drop-down menu and say type alcohol, and then it comes up. You give it how many counts of the alcohol group you want to have, and then it includes it in the query. And the structures query then is done on top of that data as well. So it's a federated query of a different system with our query engine. And then from the integration point of view, we have APIs into any aspect to our data. So we can create new data sources with a click of a button. We can destroy data sources. We can register compounds, large compound selections, calculate whatever it is. And yeah, it's very convenient from that point of view. It doesn't take specialists anymore to actually set up a chemical structure database. So once this is all said and done and you've fed your data through it, you can actually do things like this here. This is from a third-party implementation which used our data. Let's say for whatever reason you find a 25 isocholesterol. Looks like this is structure. Details don't matter. It occurs in 3 databases: Drug Bank, Drug Central, and KEBI. They have their own IDs. And to each of these IDs, there's actually data attached, right? But if you look at Drug Bank and KEBI, you don't necessarily know how they're related. So here we have a very tight relationship right away. And then you can do things like, let's look at the scaffold here with the stereochemistry, and you look at it and you find that with the stereochemistry for this framework, you find 235 instances in the data set. And the key is that it's with a click of a button, right? You don't have to write queries to get there. Then in addition, you can then look at the annotations here and say, okay, I just look at the ether compounds in this data set, or the ones which contain furans as well. And then you select these here in this tool, and then the data set gets reduced and narrowed down to where you need it to be. So you can very quickly narrow down your complex searches, your complex data into something very useful and meaningful to your query. Or on the other hand, if you have a very specific molecule in mind, you can expand your query space as well, or your data space, by clicking on the different levels of abstraction for a molecule. A little bit about semantics. There's a KEBI database, which is a semantic representation of the chemistry data. These are chemicals of biological interest. So it's not just any molecule, but they're classified here into, for example, ferropenem here is an oxalane. There's a relationship there. Is a penems. Ferropenem is a penems, and penem is a penems as well, naturally, right? But these relationships are as good and well as they are. They don't really pertain to your own data. So what we're doing with our system automatically is we can overlay through our chemical structure analytics, we can overlay your local data with this data automatically. So if you have a penem-like structure, you can see that right away through the abstractions we make, and they overlap with the data, which then is linked to KEBI, and you get all the associated data with that with a click of a button. So in a graph that looks like this, this is real data. We have PubChem here, which is a big chemistry database, has ferropenem in the data set with this identifier. We have KEBI here. KEBI has this identifier here, 3, whatever it is, with the penem structure associated. And then as you browse through the data, you see we have this fragment over here, which is a molecular graph, which is a normalized structure of the original structure. So all of these are linked to this molecule here, which is a representation of the core ring structure. And all of a sudden here, within the confines of the green circle, you have all the molecules which share this penem substructure fragment, or the ring fragment of a penem ring. You can also look at penems, of course, if they're as well. Over here, we have, I'm sorry, the blue ones here in this orientation, the blue circle, those are all the ones which have a Bemis-Mirko framework, which is the orange one here, the purple one, I'm sorry. They all share the same molecule, so the same scaffold, I'm sorry. So with the click of a button, you have all these relationships then, and you can bring this out through the graph to any one of these structures here. In this case, would go up to ferropenem and PubChem, and you know that if you search for this framework, you can find this molecule here very quickly out of PubChem, but you can also find any of the other molecules with the click of a button. And then, of course, to each of these molecules, if there are real instantiations of molecules, you have a whole slew of data which you can then link in through the data. So yeah, that's really then where the beauty of the graph comes in, and you open yourself up to do machine learning and AI on these data as well. Do we have a few more minutes, Nikhil?
Yeah, maybe a couple of more. one or two more.
Couple of more.
Yeah.
So what does this look like in real time, in the real world? Let me just look real quick. So this is our tool which we've put together, fairly simple. This is Viagra. So I can do exact match search. I search and I searched 1, 2, 3, 4, 5 databases here with different levels of context and content. This is the GSRS database from the FDA, and it has a link to Viagra as or sildenafil, I should say, which is the active ingredient of Viagra. But if I do a substructure search, I actually get another hit, which is this one here. And this one contains 2 molecules. So we have this big molecule, the sildenafil, and then here we have the citrate. So this is sildenafil citrate, also known as the blue pill or Viagra from Pfizer. So if I follow this link here from my search, I get a depiction of the core molecule at the compound level. And all of this data is calculated here. So the only input here so far was the chemical structure, except for this data over here, which I can talk about in a moment. But most important is we have 2 components here in this molecule, and they get taken apart into the individual components. And if they do exist in the database, they're actually linked to that component as well. So the citrate here is linked to the entity citrate in the database, and then the sildenafil is linked to the sildenafil as the active ingredient for this mixture up here as well. So what we haven't implemented yet, but it's a very simple graph query, is show me all the molecules where sildenafil participates in as a entity, or where citrate participates as an entity. And then we can basically explore all the questions which the FDA needs to know when they say, show me all the molecules where a parent molecule, which will be this one here, participates in a mixture or in a drug, which will be this one. So we just don't have the widget for that right now. Yeah, so that's the most important piece. And then you can just click around here and then you see, okay, we have citrate here, which comes from the GSRS database, but we also have a synonym here or an exact match, which is coming from Drug Central, which is a drug database which is available in the public domain. So these relationships are all there by default, and they're calculated, and they're just part of the data set and in the graph. So this is a little bit of the navigation in the system on the graph. I think that's all I want to show right now, and I'd be very much open to questions if there are any.
Questions from the participants? I know we are already 2 minutes above 7, but if there are questions, you can either also, there is one. Ah, thank you,
I may have a
Anissa.
question. Yeah.
Michael, go ahead.
Yeah, I have a question. Actually, you know that Matthias, the chemical space is actually growing every day. This means you need, let's say, to bring the database up to date every day. Yeah, so that so what does it mean? Because let's say you bring in new compounds and they have to run, let's say, against all the existing compounds in your database. Can you share a little bit with us? Let's say this check against the outside world. Say how massive that is, how much time actually, let's say, you need for doing this. Just a little bit on numbers. Yeah, so how big is actually, let's say, the time demand for doing this, let's say, outside world check?
So do you mean from a personal involvement or from the system involvement?
From the system involvement.
So the way we present it all the time is, so all of the big sites, they have delta updates on their data on a frequent basis, right? So I don't know, PubChem every day, several thousand compounds. Drug Central maybe once a quarter, but there are updates. So we can have FTP protocols which go out and get the latest data. We then do a comparison of the content of the file compared to the previous file, get the differences out. So that's all scripts, very simple to do. And then we push it into our API for registration. And the registration then just takes care of itself. The molecules are being queued up. And as the system has resources, they get processed yeah, in a matter of seconds. There's not much consideration to be taken based on chemical structure comparisons, because we do all the analysis ahead of time. And then once we have created our identifiers, all the work is done on the identifier, not on the structure. That's why we can get away with the graph, because there's no chemistry knowledge in the graph at all, but the whole system is really working as a registration system in the graph. Does it make sense?
Yes.
To the size, we haven't run PubChem yet. PubChem has several 60 million or 100 million compounds, I believe. Last time I checked was a while ago. What I've shown you here right now, we've just started reloading the system. There's about 80,000 molecules in there. Directly in the graph, relationships, I should say, nodes in the graph, about 80,000. In our abstracted database in the backend, where the chemical structures are managed and linked, we're looking at a factor of about 15 of that. So for every compound, we generate about 15 new compounds, but then only as duplicates come in, of course, it diminishes in the multiplication there, of course. The system is built on the Kubernetes cluster in Azure right now for our customer, and as the cluster has resources, it grows automatically.
Okay.
So that's true for the Neo database, and then some of the metadata is held in Mongo. So it's really a distributed system. On the technology side, we use Mongo for the metadata. We use the graph for the relationships and the core registration data. Not just structures, but also reactions and processes and those kind of things. And then we have a Postgres database for the structure searching, because that's not available in the graph yet.
Yeah.
And then we have a blob storage in Azure for document repositories as well.
Yeah, thanks.
Welcome.
Thank you. Thank you to. Are there any more questions? If not, I would like to steal the screen for just one moment. Yeah, I would like to thank all the participants and all the speakers for attending this session. And in case you're interested to know more about us or what do we do, please get in touch with us at these details. Thank you so much and have a nice evening. And to our US participants, have a nice day. Bye.
Thank you very much. Bye-bye.
Thank you. Bye-bye.